In calculus, an indeterminate value is a value that can be equal to any finite quantity as defined by the context in which it arises. Some examples of indeterminate values are 0 times infinity, 1 raised to the power of infinity, and 0 over 0. These are conceptual values, not real values, because they do not have a finite, determinate definition. An example of an indeterminate value arising in context is the function the sine of x over x at the point x equals 0. Because there is a 0 in the denominator of the expression when x equals 0, the graph does not exist at that point. Usually, when a function has a 0 in its denominator at some point, the graph has an asymptote, and the limit of the function as x approaches that point is infinity or does not exist. This is because such a function is approaching the conceptual value 1 over 0. The conceptual value 1 over 0 is not an indeterminate because it is always equal to infinity. But do keep in mind, both infinity and 1 over 0 are conceptual values, not arithmetic quantities. The graph of the sine of x over x does not approach infinity at the point x equals 0 because the numerator also has a 0 in it. Therefore, the function approaches the indeterminate value 0 over 0, and the limit could therefore be equal to anything. It just so happens to be equal to 1, as I shall prove in a later video. For now, let's look at something we can prove using just algebra. Consider the function x squared plus 3x plus 2 divided by x squared plus 5x plus 4. Consider its limit as x approaches negative 1. Once again, it is the indeterminate 0 over 0. To solve for its limit, we may use the first method of solving for an indeterminate, which is the method of cancelling factors of 0. Both the numerator and the denominator are factors of x plus 1, an expression whose limit is 0 as x approaches negative 1. If we factor out this expression and cancel it before plugging in, we get an arithmetic value of 1/3. Therefore, the limit of the function as x approaches negative 1 is 1/3. Notice the graph still does not exist at the point x equals negative 1, but the limit does and can be evaluated using the factored form of the function. This quality of a graph being discontinuous at a single point is called a removable discontinuity.
That was delightful.